So this is for 9-1 and 9-2. So basically the idea is you've been walking around your whole math career thinking that the entire world is made up of rectangles. Right? Whenever you graph anything in a math class, you've graphed it in what we call rectangular coordinates. Or sometimes we call these Cartesian coordinates. Rectangular is a little more descriptive. And the way rectangular coordinates work is if you want to describe a point, x, y, you basically pretend that it's the corner of a rectangle made with the origin. Right? You pretend that this point is on the corner of this rectangle. And then you give me x as the width of the rectangle and y as the height. Right? One of them, I guess this will be length and width if you want to do it. Right? But one of these is the length of the rectangle, and one of these is the width. That's the coordinate system we've used. And it turns out that that's a really good coordinate system for things that look like rectangles, like lines. Right? Lines look like rectangles, kind of. So this works out pretty well. It's kind of a crappy coordinate system for things that don't look anything like rectangles, like circles. Okay? So to graph things that have more curvature to them, like a circle, it turns out a different coordinate system is a little more handy. That coordinate system is called polar coordinates. So instead of pretending that each point is on the corner of a rectangle, you pretend that each point is on the perimeter of a circle, on the outside of a circle. The circle would center at the origin. So this point, for example, would be on a circle that looks something like this. A little bigger than I want it. It's like a circle. Or pretend. Right, so every point can make a circle with the origin where you just designate this distance the radius of the circle. So then to describe a point, you say, well, what radius circle is it on? And what angle have you gone from the x-axis? Positive x-axis. So this we'll call theta. Or theta is the angle made with the positive x-axis. So in rectangular coordinates, you label your point x comma y, where the x is the length of the rectangle and the y is the width. Here you're going to label your coordinate r comma theta, where r is the radius circle that the point lands on, and theta is how far you have to go from the positive x-axis to get to that point. Yeah. Oh, okay, that's kind of interesting. Let me not say anything about that.
Yeah, skip that.
Skip that.
Yeah.
Skip, down, down. Let's just do the example, and then it'll become evident. So just to get you used to this, let's graph some points. Ultimately, what we want to do is graph in polar. Okay, we want to see if these coordinates can help us get some very pretty graphs, more pretty than we used to. But if we want to be able to graph in polar, we first have to plot single points in polar. So I gave you, looks like 4 points. And I gave you a little grid there. And I want to plot them. So on the grid below, plot and label each point. So point A is 1 comma pi over 2. So what does this mean? I gave you polar coordinates, 1 comma pi over 2. How would I graph that? 1's the radius. Pi over 2 is the angle. The angle is always measured from the positive x-axis. It's always in standard position, just like usual. So this will be my theta. This will be my r. So basically I have a circle of radius 1. So that'll be my first circle on that diagram there. I know my point is on a circle of radius 1, and then the pi over 2 tells me that starting from this axis, I need to go pi over 2 to get to my point. So this guy right here is A. In polar coordinates, the origin has a different name. It's called the pole. Kind of like the North Pole. You can think of this almost like latitude and longitude. If you're familiar with that. And then the positive x-axis has a different name as well. It's called the polar axis. I probably will never use these words, but if you see them, that's okay. I will still probably use origin and positive x-axis just because my brain hasn't been trained in polar as well as it should have been. So that's if you have two positive values, positive radius, positive angle. What do you think changes if I make my angle negative? How would I graph 3 comma negative 7 pi over 4?
We should have a circle with the...
Yeah, so first of all, you have your radius, right? 1, 2, 3, 1, 2, 3, 1, 2, 3.
And then you go clockwise to 7 pi over 4.
Yeah, so now that we have a negative angle, you measure it like we normally measure negative angles. Instead of going counterclockwise, you go clockwise. 7 pi over 4. 7 pi over 4 is almost 2 pi, and it's going to cut here. So my point is right there. It's in the first quadrant. Out on a circular radius 3, we went an angle of negative 7 pi over 4. All pretty good? Pretty standard? Everything's okay? Haven't offended anybody? I offended you, yes.
So on these you have to draw the arrow in which direction the angle is going.
You don't have to, but you got to get the right quadrant, really. I mean, you should draw the arrow, but you're starting from the positive x-axis as long as you end up in the first quadrant. So what do you think happens with a negative radius?
Would it not change anything?
Would it not change anything?
Is it we kind of treat it like an amplitude. Am I looking at that the wrong way?
Well, think of radius kind of like you think of x and y values. Right over here in the xy plane, which we don't live anymore, if I gave you the point -3, -2, what do the negatives do? They give you a direction, right? They say instead of going 3 in this direction, go 3 in this direction. And instead of going 2 up, go 2 down. So you want to think of the negative radius in the same manner. You're still going to be on a circle of radius 2. Right, so that's true. That doesn't change. The fact that you land on a circle of radius 2 is still the same. But now when you go to the angle 4 pi over 3, where does 4 pi over 3 land?
Negative 4 pi over 3.
So 4 pi over 3 usually lands in the third quadrant, which is down here. But instead of going out your radius 2 in this direction, you go back in this direction. Right? So think of this as kind of our axis. Normally we would go out 2 units on the r-axis like this. 1, 2. What I'm saying is if you go in the exact opposite direction, so make a line here, a straight line with angle 180, angle pi between the 2 rays, and then go out 2 units in this direction. 1, 2. This will be your point. So 4 pi over 3 brought me to the 3rd quadrant, but the fact that my radius was negative pushed me back on a straight line into the 1st quadrant.
I have a question.
Yes?
Will you explain the negative 7 pi over 4 again, please?
What part of it?
I'm just confused by it. I'm just asking you to re-explain it. Maybe I'll get it.
But I'm asking, you understand the negative part, the fact that it's going this way or not? So negative on an angle tells you whether to go down or up when you start.
Yeah.
Okay. So now the fact that it's 7 pi over 4, if you remember from, I don't know, years ago it seems, 7 pi over 4 means you break pi into 4 equal sections and go 7. 1, 2, 3, 4, 5, 6, 7.
Oh, okay. And that's how you landed at B?
And that's how I landed here, yeah. And then B is the point that's on this circle of radius 3. Right, so the negative 7 pi over 4 gives me this entire ray here. Right, it gives me this whole thing. This all is negative 7. That whole thing is the ray at negative 7 pi over 4. But then B is the point that is 3 on a circle of radius 3. So
Okay.
I go out 1, 2, 3, and I get 8.
Okay.
So what about our last one here where we have 2 negatives? Negative 3, negative 7 pi over 6. How do we graph this guy?
So you start with the graph of radius 3.
Yeah, so for a second, ignore the negative on the radius. Right, just go out and draw your radius 3 circle. It looks something like this. Okay. Now, starting from the positive x-axis, or the polar axis, form an angle of negative 7 pi over 6. So where's negative 7 pi over 6 going to land? So negative 6 pi over 6 would be right here. Right? Negative pi, negative 6 pi over 6 would be right here. You go a little bit more. Now, if I had a radius of positive 3, that would give me my point. Right? That's the guy that you would get if you had a radius of r equals positive 3. But we don't. Boo-hoo. So what do? You flip. You go the exact opposite direction. So you go down into the 4th quadrant, like this, and you go 3 units. So add on to the circle of radius. So this is the point that we labeled. One of the slightly confusing things about polar coordinates is that points have more than one representation. Like in the xy plane, if I say negative 3, negative 2, that's the only way to get to negative 3, negative 2. But here, for example, can you give me another set of coordinates that would land me here? So give me, with radius positive 3, if I wanted to use a radius of positive 3, how would I get here? You could do negative pi over 6, right? If you went negative pi over 6, that would work. 11 pi over 6 would also work if you wanted to keep everything positive. Right? 3 comma 11 pi over 6, because then you would go this way. Now it's still ending here. So that's, whatever, you have all these choices. For the most part, every point in the plane can be represented using angles between 0 and 2 pi. It can be represented uniquely. You have to be careful with the pole. If I wanted to write coordinates for the pole, for the origin, what coordinates would I use?
0, 0.
So for the pole, I could use 0 for the, I have to use a 0 radius, because if I have radius bigger than 0, I'm going to go away from the pole. What about for the angle? Doesn't matter. If you're not going out anywhere, it doesn't matter which direction you don't go anywhere. Right? So the pole is going to be 0 comma anything, any number at all. Right? So every other point can be represented uniquely between 0 and 2 pi using an angle between 0 and 2 pi, but the pole you can get with any angle. 0 pi over 2, 0, 3 pi over 2. I'll give you the pole. But 0, 0 might be an easy one to agree upon. Anyway, so on Wednesday, I guess I'll see you. I have a bunch of quizzes to pass back, and I'll talk more about graphing polar a little bit.